Welcome back to the deep dive, everybody. Today, we're going to be jumping into a topic that, on the surface at least, might feel pretty familiar, maybe even a little bit like going back to high school geometry class.
Yeah, back to the basics.
Yeah, exactly. We're going to be talking about the relationship between lines and circles when they're hanging out together on the same plane, but stick with us here.
Oh, yeah.
Because while this might sound like well-trodden territory, there's actually a lot of really cool stuff, surprisingly elegant concepts, and even some really practical applications hidden within this seemingly simple relationship. So we're going to dive deep, see what we can uncover.
Absolutely. And when we talk about a line in a circle meeting, we're really talking about, uh, you know, three basic scenarios.
Right.
It's kind of like a choose your own adventure here. The first one is they just completely miss each other, right? The line just goes sailing on by the circle. They've got nothing in common, no points shared. That's our non-intersecting line. Door number two, the line goes right through the circle like a well-aimed dart, hits it in two distinct spots. That, my friend, is what we call a second.
Yeah.
But door number three, and this is the one we're really focusing on today, is when the line just barely grazes the circle, makes contact at a single solitary point.
The gentle touch.
Precisely.
Yeah, and that's what we call a tangent, right? It's a line that intersects the circle at only one point. Now, I know this might sound kind of abstract when we're just talking about it, but think about it this way. Think about imagine a rope going over a pulley. Like when you're drawing water from a well, you've got that, bucket down there and you're pulling it up. The rope on either side of that pulley where it touches, it's like a tangent, right? And just grazing the circular edge of that pulley at one single point.
Perfect example. Or how about a bicycle wheel moving along the ground?
Yeah.
Think about that for a second. At any given moment, you've got that one tiny patch of tire that's in contact with the road, right?
Yeah.
That's the point of contact. And that ground, the road itself, acts as a tangent to the circular wheel at that exact spot. So, I mean, you see, these ideas, they're not just, theoretical. They're like happening all around us all the time.
Yeah, constantly, all the time. And speaking of, bringing these concepts to life a little bit, it's kind of fun to think about where the word tangent actually even comes from. It actually comes from the Latin word tangere, which means to touch. And it was first coined way back in 1583 by a mathematician named Thomas Finke.
Oh, wow. So got some history to it.
Yeah, a little bit of historical context there. And so that special point where the tangent and the circle meet, that's called the point of contact.
Right. It's a very important point.
Yeah.
Literally.
Absolutely. All right, so we've got our definition of a tangent down. Now let's unpack how these tangents actually come into being. How do we even find them? Our source material talks about this cool activity, activity one, that uses a circular wire and a straight wire that's kind of pivoted at a point on the circle. So imagine you can rotate that straight wire around like it's fixed to the circle at one spot and you can swing it around.
Right. You can just spin it.
Exactly. What do you think happens as you do that?
Well, as you're spinning that straight wire, you'll find most of the time it's going to be cutting through that circular wire at 2 points.
Right. Our second.
Exactly. Good old second showing up again. But there's going to be this one very specific position, and it's shown as A prime, B prime in figure 10.3 in our source material, where that straight wire just barely touches the circle at a single point, which they call P, boom, tangent in action. But, keep rotating, and you're back to those two intersection points. And what this does is it gives us this really cool visual confirmation, right, that at any given point on a circle, it seems like there's only one unique line that can act as a tangent.
Yeah, just one. It's so specific.
Absolutely.
So here's where it gets even more interesting, right? So think about that second line in this activity as it gets closer and closer to becoming a tangent, like you're slowly rotating it towards that tangent position. What happens to those two intersection points where the second is cutting through the circle?
Well, they're getting closer and closer together, right?
Yeah.
Until at that precise moment when it becomes a tangent, they merge.
Yeah, they become one.
They're like, they're chasing each other, and then bam, they're the same point.
It's like a little collision.
Exactly. So really what we're seeing is that a tangent is kind of a special case, like the ultimate outcome of a second, where the two ends of that chord, remember the chord is the line segment, connecting those two intersection points, they've basically gotten so close that they've become the same point.
Yeah, so it's like second, but taken to the extreme.
Yeah, taken to the limit.
Love it. Okay, so activity 2 offers another way to visualize this whole tangent situation. Imagine you've got your circle and you've drawn a second cutting through it. Now, picture drawing lines that are parallel to that original second, but on either side of it.
Okay, I can see that.
What do you think happens as you draw those parallel lines further and further away from that original second?
Well, the chord that those parallel lines are making inside the circle, that's going to get smaller and smaller as the lines move away.
Yeah, exactly.
Until eventually, on each side, you're going to hit a line that just grazes the circle at a single point.
Bingo.
Tangent city. And those are your tangent lines that are parallel to that initial secant. So what we're seeing here is that for any given secant that cuts through a circle, you can have at most 2 tangent lines that are parallel to it.
Right, one on each side.
Exactly. Which, again, just drives home how unique these tangent lines really are. They have to be in just the right spot.
So specific, yeah. All right, let's shift gears a little bit and talk about something that's super fundamental to understanding tangents, Theorem 10.1. This theorem states that the tangent at any point on a circle is always perpendicular to the radius drawn to that point of contact. This is like a cornerstone of tangent knowledge, real time.
This is a rule you got to know.
Yeah, so let's break it down, make sure we really get it.
Yeah.
Imagine your circle, and we'll mark its center as O, like we always do in geometry. Now, picture a tangent line touching that circle at a point we'll call P.
Okay, got it.
Theorem 10.1 says that if we draw a line straight from the center O to that point of contact P, which is our radius OP, that radius will always meet the tangent line at a perfect 90-degree angle. It's a perpendicular intersection. They form that classic L shape right there at the point of contact.
Right, right. And there's a really nice logical reason for why this is always true.
Oh, I love a good logical reason. Lay it on me.
Okay, so let's pick any other point on that tangent line, a point different from P, and we'll call it Q. Now, if we connect Q to the center O, making a line segment OQ, that point Q has to be located outside of the circle.
Has to be.
Has to be. Because if it were inside, our line would be cutting through the circle at more than one point, which would make it a secant, not a tangent.
Right, that's how we define them.
Exactly. So because any point Q, other than P, of course, on that tangent line is outside the circle, the distance from the center O to Q has to be greater than the distance from O to P, which is just the radius. This is true for every single point on the tangent line except for P.
Because P is like the closest point on the line to the center.
Exactly. It's the shortest distance. And now, if you remember your basic geometry, the shortest distance from a point to a line is always the perpendicular distance. That's like a fundamental concept.
Like dropping a plumb line.
Exactly.
Yeah.
So since OP is the shortest distance from O to any point on that tangent line, it has to be perpendicular. It just logically follows.
So elegant.
Beautiful, right?
And this whole perpendicular relationship, it might seem simple, but it leads to some really important conclusions. First, it means that at any single point on a circle, you can only have one tangent line, right?
Makes sense.
If there were another line through that same point that was also perpendicular to the radius, well, it would have to be the exact same line.
Right. There's only one way to be perpendicular at that point.
Second, this theorem introduces another handy term, the normal. The line that goes along the radius extending through the point of contact is called the normal to the circle at that point.
And this normal line, it's not just a geometry thing. It's actually super important in physics and engineering, especially when you're dealing with forces acting on curved surfaces, like a key reference direction.
Yeah, totally. Okay, let's think about something else now.
Mm-hmm.
How many tangent lines can we actually draw to a circle if we start from a given point somewhere out in the plane? Our source material, Activity 3, gets into this, and it all depends on where that point is located relative to the circle.
So we've got 3 possible scenarios.
Okay, let's break them down. Scenario number 1. What if our point, we'll call it P again, is located inside the circle?
Inside the circle.
Yeah, right.
They smack dab in the middle.
In that case, you're not going to be able to draw any tangents from that point to the circle.
None. Right.
No, any line that you try to draw through that point is going to have to cut through the circle in 2 spots to get out to the other side.
Yeah, it's always going to be a secant.
Always a second. No tangents allowed inside the circle club.
Right. Okay, scenario number 2. What if P is right on the edge of the circle? Well, we've been talking about this all along. At any point that's on the circle itself, you can draw exactly one tangent line right there at that point.
The one and only.
That's it.
Okay, last scenario. P is outside the circle, somewhere out there in the plane beyond the circle's edge. What happens then?
Now things get interesting. In this case, you can draw exactly 2 distinct tangents to the circle, both passing through that external point P.
2 tangents, 2 points of contact.
Precisely. And you can see this illustrated in figure 10.63 in the source material.
And When we have these two tangents coming from an external point P and touching the circle at points we'll call T1 and T2, we can talk about the length of those tangents, right? It's just the distance along that tangent line segment from the external point P to the point where it touches the circle, so PT1 and PT2.
Right, just measuring those line segments. Now, a natural question that comes up is there any relationship between the lengths of those two tangents? I mean, they both come from the same external point. Are they connected in some way?
Good question. And Theorem 10.2 gives us the answer. The lengths of tangents drawn from an external point to a circle are always equal.
Always.
Always equal. It's a beautiful thing. And the proof for this involves some classic geometry, specifically the idea of congruent triangles. So picture this. We've got our circle with center O, our external point P, and those two tangents, PQ and PR, touching the circle at points Q and R. Now, if we draw lines connecting the center O to those points of contact Q and R, those are our radii OQ and R, and we also connect P to O with a line segment, we've created two triangles. Triangle OQP and triangle ORP.
Okay, I'm visualizing it.
Now remember, our trusty theorem 10.1, that told us that the radius is always perpendicular to the tangent at the point of contact, right?
Right, the perfect L shape.
Exactly. So that means angles OQP and ORP are both right angles, 90 degrees. We also know that OQ and OR are both radii of the same circle, so they're equal in length. And of course, the line segment OP is a shared side by both triangles.
So we've got two right triangles, same hypotenuse, one other side that's equal, which means we've got ourselves a perfect setup for the RHS congruence rule. Right angle, hypotenuse, side. This tells us that these two triangles are congruent, meaning they're basically identical copies of each other. And if the triangles are congruent, then all their corresponding sides and angles have to be equal.
So PQ and PR, those tangent lengths, they must be equal.
Exactly. And there's actually another clever way to prove this using the Pythagorean theorem. Since we have those right triangles, we know that PQ squared is equal to OP squared minus OQ squared, and similarly, PR squared is equal to OP squared minus OR squared.
Right, Pythagorean theorem in action.
Since OQ and OR are equal, they're both radii, it directly follows that PQ squared has to equal PR squared, and therefore PQ equals PR.
Two paths to the same conclusion.
Precisely. And there's one more neat little detail that comes out of this whole congruence thing. Because triangles, OQP and ORP, are congruent, all their corresponding angles are equal too. Specifically, angle OPQ is equal to angle OPR. What does this mean? It means that the line OP, connecting the external point P to the center O, it's actually bisecting the angle formed between the two tangents, angle QPR.
So the center of the circle is always on the line that perfectly splits the angle formed by those two tangents.
Exactly. All right.
Okay, let's put some of these ideas into practice with some real examples. Example 1 from the material deals with concentric circles, which are circles that share the same center but have different radii, like a bullseye.
Right. Yeah.
The problem asks us to prove that if we have a chord of the larger circle that just happens to touch the smaller circle, so it's a tangent to the smaller circle, the point where it touches that smaller circle will also be the midpoint of that chord. So the chord is bisected at the point of contact.
And the solution is so elegant. Imagine our two concentric circles, same center, we'll call O again. The larger circle's got a chord, we'll call it AB, and this chord just grazes the smaller circle at a single point P. Now, if we draw a radius from O to that point P on the smaller circle, Theorem 10.1 tells us that OP has to be perpendicular to that chord AD at P.
Right. Tangent and radius, always perpendicular.
Always. Now, if we focus on the larger circle for a moment, AB is just a chord in that circle, and we've got this line OP coming from the center of the circle, and it's perpendicular to the chord.
Classic geometry setup.
Classic. And one of the fundamental properties of circles is that any line drawn from the center of a circle that's perpendicular to a chord will always bisect that chord.
And right in half.
Exactly. Therefore, point P, where OP meets AB, must be the midpoint of AB. AP equals BP. Boom, problem solved.
Beautiful. Okay, example 2 gives us a scenario where we have an external point, we'll call it T, and two tangents, TP and TQ, drawn from this point to a circle with center O. We need to prove a relationship between the angle formed by those two tangents, angle PTQ, and the angle formed by one of the tangents and the radius drawn to the point of contact, angle OPQ. Specifically, we want to show that the measure of angle PTQ is exactly twice the measure of angle OPQ.
Okay, let's break it down. We'll call the measure of angle PTQ theta. We know from Theorem 10.2 that the lengths of those tangents, TP and TQ, are equal.
Equal tangents.
Right, which makes triangle TPQ an isosceles triangle.
Two sides equal, two angles equal.
Exactly. So angle TPQ equals angle TQP, and each of those angles would be 180 degrees minus A divided by 2, which simplifies to 90 degrees minus A over 2.
Okay, I'm following.
Now let's bring back theorem 10.1. Remember, radius OP is perpendicular to tangent TP at the point of contact P. So angle OPT is a right angle 90 degrees. That means angle OPQ is the difference between angle OQT and angle TPQ, which is 90 degrees minus over 2.
A little bit of algebra there.
A little bit, but when you simplify that, you get A over 2. And since we defined A as the measure of angle PTQ, we've shown that angle OPQ is half the measure of angle PTQ, or put another way, angle PTQ is twice the measure of angle OPQ.
Nailed it. Okay, last example. Example 3 gives us some concrete measurements to work with. We've got a chord PQ inside a circle with a radius of 5 centimeters, and the length of the chord is 8 centimeters. Tangents are drawn at points P and Q, and they intersect at an external point T. Our mission: find the length of tangent TP. Figure 10.10 in the material shows us what this looks like.
All right, let's do this. We'll start by drawing a line segment from the center of the circle O to the point where it intersects chord PQ, and we'll call that intersection point R. Because the tangents from T to P and Q are equal in length, triangle TPQ is isosceles, and that line OT we drew, it's going to bisect both angle PTQ and chord PQ. And importantly, it will also be perpendicular to PQ.
Right, so it's cutting everything neatly in half.
Exactly.
Okay.
So segments PR and RQ are each half the length of PQ, so they're both 4 centimeters long.
Got it.
Now we've got this right triangle, OPR, with OP being the radius, 5 centimeters, and PR being 4 centimeters. We can use the Pythagorean theorem to find the length of OR, or squared plus PR squared equals OP squared. Plugging in our numbers, we get OR squared plus 4 squared equals 5 squared, which simplifies to OR squared plus 16 equals 25. So OR squared is 9, and that means OR is 3 centimeters.
Okay, we're getting close.
Now we're going to use the idea of similar triangles. Remember those?
Vaguely. Refresh my memory.
Similar triangles are triangles that have the same shape, but maybe different sizes, and their corresponding sides are proportional. So look at triangles TRP and PRO-O. They both have a right angle, and they share an angle at T. Angle PPR in the bigger triangle is related to angle RPT in the smaller one, and angle RPO is complementary to angle TPR. So they are similar.
Okay, similar triangles, proportional sides. Got it.
Because of that proportionality, we can set up this equation. TP divided by PO equals RP divided by rho. Plugging in the values we know, TP divided by 5 equals 4 divided by 3. Solving for TP, we get TP equals 5 times 4 divided by 3, which is 203 centimeters.
So the length of tangent TP is 203 centimeters.
Nice. And the source material mentions another way to solve this, using the Pythagorean theorem twice, setting up a system of equations. Right. A bit more algebraically intensive, though. I think that the similar triangles approach is a bit more elegant for this particular problem.
Agreed. So wrapping up our deep dive today, we've really explored this fascinating world of tangents, these lines that have that unique relationship with circles, just touching at a single point. We've seen how they relate to seconds, those lines that cut through the circle, and we've delved into that super important rule that the tangent is always perpendicular to the radius at the point of contact.
And we've explored how many tangents you can draw from a point, depending on its location inside, on, or outside the circle. And of course, that really cool fact that tangents from the same external point are always equal in length.
And as we mentioned at the beginning, these aren't just theoretical ideas. Tangents are everywhere in the real world, from pulleys and belts to the way wheels interact with the ground.
Absolutely. Tangents in action. It just goes to show how these fundamental geometric principles are constantly at work all around us.
Which brings us to a final thought for you to ponder. We've been talking about tangents to circles, but what about other shapes, like ellipses or parabolas?
Oh yeah, those curvy shapes.
How would we even define a tangent to a shape like that? Would those tangents have unique properties, too? There's a whole world of geometric exploration out there just waiting to be discovered.
A whole world of tangents.
Exactly. And on that note, we'll wrap up our deep dive into this fascinating relationship between tangents and circles. We hope you enjoy this exploration, and maybe it's even sparked some curiosity to learn more.
Thanks for joining us.
Until next time, happy exploring.